Welcome to lecture 45. We are talking about flow measuring instruments. So, this is the last lecture of this week. We have talked about constant area variable pressure drop meters, we have talked about variable area constant pressure drop meter. So, today we will talk about velocity measurement type, mass flow measurement type, positive displacement type, and also we talk about wear type flow meters which are used for flow of fluids in open channel. So, under velocity measurement we will talk about hot wire anemometer. Under mass flow measurement type we will talk about Coriolis mass flow meter. Under positive displacement type we will talk about rotating disc, and for flow of fluids in open channel we will talk about wear type flow meters. What you see are images of hot wire anemometer. The hot wire anemometer is used to measure fluid velocities by measuring heat loss by convection from a very fine wire which is exposed to the fluid stream. The wire is electrically heated by passing an electrical current through it. When the heated wire is cooled by fluid stream, its electrical resistance decreases because the resistance of metal wire varies linearly with temperature. Instead of hot wire, we can also have hot thin film. There are two basic forms of hot wire or hot film anemometers, and both utilize the same physical principle, constant current type and constant temperature type. Let us first talk about constant current anemometer. In this case, the current through the wire is kept constant and it is exposed to the flow. When the flow takes place over the hot wire, changes in temperature and resistance occur. So, when the flow takes place over the hot wire, there will be changes in temperature and accordingly there will be changes in resistance. The wire attains an equilibrium temperature when the I square R heat generated is balanced by the convective heat loss from the wire surface. So, since a current is flowing through the resistance wire, there will be heat generated whose amount will be equal to I square into R, where I is the current flowing through the wire and R is the resistance. Now, the hot wire is exposed to the fluid. So, there will be convective heat loss from the wire surface to the fluid medium. So, the wire will assume an equilibrium temperature when there is a balance between the heat generated, that is I square R heat generated, and the convective heat loss from the wire surface. The circuit is so designed that I square R is constant. Thus, wire temperature adjusts itself to change the convective heat loss till equilibrium is reached. The convective heat transfer coefficient is a function of flow velocity. Thus, the equilibrium wire temperature is a measure of flow velocity. So, this is to be understood that the convective heat transfer coefficient is a function of flow velocity. In fact, this is given by King's law. Thus, the equilibrium wire temperature is a measure of flow velocity, because the convective heat transfer coefficient will dictate the equilibrium temperature of the wire, because the equilibrium temperature wire will depend on the I square R heat generated equal to convective heat loss from the wire surface. So, equilibrium temperature will be established when I square R heat generated equal to the convective heat loss from the wire surface. Now, the convective heat loss will depend on the convective heat transfer coefficient. Now, convective heat transfer coefficient depends on the flow velocity according to King's law. So, the flow velocity also decides what will be the temperature of the hot wire anemometer. The temperature or the equilibrium temperature of the wire can be measured in terms of electrical resistance, because if the temperature changes, resistance changes. So, I can measure the temperature by measuring the resistance using a bridge circuit using Wheatstone-Bridge principle. So, the resultant change in voltage can be now calibrated in terms of in terms of velocity. Constant temperature anemometer. In this case, the current through the wire is adjusted to keep the wire temperature constant. Again, the wire temperature can be measured in terms of its electrical resistance. The current required to keep the temperature or the resistance of the wire constant is then a measure of flow velocity. So, you can see that both the constant current type anemometer and the constant temperature type anemometer basically uses the same principle, but in a different way. So, this is the energy balance I square R RW. RW is the wire resistance and I is the wire current. So, I square RW is the heat generated, and the convective heat loss from the wire surface is heat transfer coefficient H multiplied by the area of heat transfer into the temperature difference between the wire and the surrounding fluid. So, Tw is the temperature of the wire and Tf is the temperature of the flowing fluid. So, energy balance I square R is H into A into Tw minus Tf. The King's law relates heat transfer coefficient with the flow velocity according to this expression, where V is the velocity, H is the convective heat transfer coefficient, and small a, small b are constants. So, this is the sensor. So, this is the thin wire which is approximately 1 millimeter long, and it has a diameter say approximately 5 micrometer. In fact, the diameter varies between 2.5 micrometer to 10 micrometer. So, this is the sensor, which is nothing but a thin wire, maybe a thin platinum wire, and you have the wire support. So, electric current flows through the wire. So, there are different designs. And this one goes to one arm of the Wheatstone bridge. The material of the hot wire can be platinum, it can be tungsten, or it can be platinum rhodium. Response to fluctuation depends on wire diameter. Smaller the diameter, faster is the response. The diameter is small, normally in the range of 2.5 and 10 micrometer. Typically 5 micrometer is often used, but smaller the diameter, faster is the response. So, this is an arrangement using bridge circuit for measurement of flow velocity. So, I have attached the hot wire anemometer as one arm of the Wheatstone bridge. So, this is the galvanometer whose readings will be used to relate to the flow velocity. So, the current versus velocity relationship is linear. When I plot I square versus square root of velocity. The advantages of hot wire anemometer: it can measure rapidly fluctuating flow, very small in size, no moving parts. They pose little obstruction to flow. They have a low thermal time constant. They are very cost effective along with good longevity. Micro machined anemometers are now widely used in automobiles for the measurement of air intake mass. Next, we will talk about Coriolis mass flow meter. What you see is an image of a Coriolis mass flow meter. These are very accurate flow meters, but more expensive than several other types of flow meters. The principles are based on Coriolis force. So, let us first try to understand what is Coriolis force. If a body moves with a translational velocity v on a surface that rotates with an angular velocity w along a direction perpendicular to v, then the body experiences a force which is 2 times m into w cross v that acts along the third direction in the right handed orthogonal coordinate system. This force is called Coriolis force. Here m is the mass of the body. This Coriolis force is named against Gaspard de Coriolis. Thus, an object moving with a constant velocity above or on the surface of the earth in a generally northerly or southerly direction will be deflected in relation to the rotating earth. Coriolis type mass flow meters use this force to produce a deflection of an arm of a U-shaped flow tube. The Coriolis force is extremely important in several branches of science, for example, in atmospheric science. So, when fluid is passed through a U tube or U bend, so you have one U bend, I have another U bend. So, this is a design where two U bends have been used. There are designs of Coriolis mass flow meter which uses a single bend, single U bend. In fact, there are several other geometries also possible. When fluid is passed through a U bend, it imposes a force on the tube wall perpendicular to the flow direction. This is Coriolis force. The deformation of the U tube is proportional to the flow rate. Coriolis meters are expensive but highly accurate. So, note that there are two U-bends here. The flow through this pipe is in this direction and this has been attached to the pipe through which flow is moving. So, there is this driver units and there is these two sensors. We will now see the role of this driver unit and these sensors in the next slides. So, this is the connections to the pipe through which fluid is flowing. Again, we are looking at a design which has two U-bends. So, this is one flow tube, this is another flow tube. So, this is the drive coil. This produces vibrations in each tube and this is one sensor, this is another sensor. They are called peak-off coil. We will see what they do in the next slide. Here you have flow divider. What it does is it divides the flow that is flowing through this equally to this tube and this tube. So, process fluid enters the sensor and flow is divided with half the flow through each tube. An electromechanical drive unit positions midway excites vibrations in each tube at the tube resonant frequency. The tubes are vibrated in opposition to each other and they oscillate at their natural frequency midway from here to here. So, these two tubes, these two sensor flow tubes are anchored here. So, this is midway from this anchor and this anchor, and there are two peak-off coils which are basically sensors. Tubes are made of various materials and stainless steel is very common. Tubes are also manufactured in different geometries such as B shaped, D shaped, U shaped, triangular shaped, helix shaped and straight. The vibrations in the two tubes are such that in the absence of flow, the inlet and outlet sections vibrate in phase with each other. Two sensors which we call peak-off measures the phase difference between these two sections. So, those two peak-off coils or two sensors measure the phase difference between these two sections. In presence of flow, the vibratory motion of each tube causes forces on the particles in the flowing fluid. These forces induce motion of the fluid particles in a direction that is orthogonal to the direction of flow, and this produces a Coriolis force. The Coriolis force causes a deflection of the tube that is superimposed on the top of the vibratory motion. So, in presence of flow, the vibratory motion of each tube causes forces on the particles in the flowing fluid. This vibratory motion was caused by the drive coil. So, the drive coil causes the vibratory motion, and these two peak-off coils measures the phase shift between these two vibrations in these two sections. In presence of flow, the vibratory motion of each tube causes forces on the particles in the flowing fluid. These forces induce motion of the fluid particles in a direction that is orthogonal to the direction of flow, and this produces a Coriolis force. This Coriolis force causes a deflection of the rate of the tubes that is superimposed on the top of the vibratory motion. When there is no flow through the tube, there is no Coriolis effect and the sine waves are in phase with each other. So, this Peikoff coils will measure the phase shift between these two sections. So, you have inlet Peikoff, you have outlet Peikoff, and when there is no flow through the tube, there will not be any Coriolis effect and the sine waves are in phase with each other as shown in the figure. See, both are in phase with each other. When fluid is moving through the sensor's tubes, Coriolis forces are induced, causing the flow tubes to twist in opposition to each other. The time difference between the sine waves is measured and this is directly proportional to the mass flow rate. So, when there is fluid flowing through the tubes, there will be development of a Coriolis force. This Coriolis force will cause a deflection in the tube and these flow tubes will twist in opposition to each other. The time difference between the sine waves is measured and it is directly proportional to the mass flow rate. So, there will be a phase shift. There will be a phase shift which can be measured in terms of the time difference, and this is directly proportional to the mass of the fluid flowing through the sensor. So, this time difference or phase shift is directly proportional to the mass flow rate. So, this is what happens when you have flow through the sensor tube. So, this is the same when there is no flow, there is no Coriolis effect, but when there is flow, there is Coriolis effect. There is no phase shift here, but there is a phase shift here. So, this time difference is directly proportional to the mass flow. There are various geometries, B type, D type, U bend, triangle, helix, straight. Most implementations use a pair of counter vibrating tubes to cancel the effect of external vibrations. Advantages and disadvantages of Coriolis mass flow meter. Advantages: direct mass flow measurement unaffected by variations in fluid properties. Coriolis mass flow meter also measures density. High accuracy can be obtained. The typical accuracy is plus minus 0.1% to plus minus 0.3%. Low maintenance cost, available in a range of corrosion resistant measuring tube materials. Disadvantages: initial cost for a Coriolis mass flow meter is high, limitation in size. Flow measurement by positive displacement type flow meter. We will talk about notating disk meter. Positive displacement flow meters are direct measurement meters. They measure volumetric flow by separating the flowing stream into distinct portions and provide an output directly proportional to the number of portions which pass through the meter. Notating disk flow meters operates on notating disk principle, where a disk notates about the vertical axis to allow to pass a certain amount of fluid. It is most probably the most commonly encountered flow meter found throughout the world for commercial, utility and industrial applications. The meter is of particular importance in the measurement of commercial and domestic water. Note that notating disk is not same exactly rotating disk. So, the disk is notating, that means while it is rotating, it is swaying. Oval is another term used for notating. Notating disk meters are in the form of a disk that oscillates, allowing a known volume of fluid to pass with each oscillations. These oscillations can be counted to determine the total volume. So, this is the disk which oscillates or notates, and it allows a known volume of liquid to pass through it with each oscillations. So, if I count these oscillations, I can determine the total volume. It can also be set up to measure the total flow by tracking the velocity and knowing the cross sectional area of the meter to totalize the flow. The notating disk meter is probably the most commonly encountered flow meter. Notating disk meter are used for petroleum fuel such as furnace oil, light diesel oil, high speed diesel, kerosene, etc., and final liquids such as solvents, acid, dispersants, paints, etc. The meter is of particular importance in the measurement of commercial and domestic water. The common sizes for notating disk meters are 0.5 inch, 0.75 inch, 1 inch, 1.5 inch and 2 inches. They can deliver flows in the range of 76 liter per minute to 600 liter per minute. Industrial notating disk meters provide accurate measurements for low flow meters and are relatively easy to install and maintain. Depending on the construction materials used, the notating disk meter can handle a wide range of chemicals such as acids, slurries, etc. The useful temperature range is from minus 150 degree Celsius to 120 degree Celsius. Finally, we will talk about flow in open channel and we will talk about wear. What you see is some images of flow through open channel. So, what is flow through open channel? So, during flow in open channel, the liquid has free surface. There are natural flows in open channel, there are artificial creation as well. So, examples of flow in open channels are tunnels, partially filled pipes, canals, streams, rivers, etc. There are several useful applications of flow meters in flow in open channels such as power stations, municipal water works, sewage disposal units, water irrigation projects, etc. We will talk about a flow meter called wear, which can be used to measure volumetric flow rate in flow in open channel. A wear is a overflow structure built across open channels to measure volumetric flow rate. Basically, it is an obstruction in the channel so that liquid backs up behind and then overflows. When the napkin discharges freely into the air, a hydraulic relationship exists between the head and the flow rate. So, that helps me to find out the flow rate. This snap is basically this. So, when nap discharges freely into the air, a hydraulic relationship exists between the head and the flow rate. So, we can measure the head, this is a pressure head we can measure, and then since there is a relationship that exists between the head and the flow rate, I can measure the flow rate. V-notch wear, the V-notch wear is used with the apex of the triangle downward. This is the apex of the V-notch wear. So, V-notch wear is used with the apex of the triangle downward. The notch angle, which is theta here, varies in the range of 22.5 degree to 90 degree. V-notch wear is used for measurement of small flow rates with good accuracy. An accuracy of plus minus 2% can be achieved. So, this is a relationship that relates the volumetric flow rate with the head H in case of V-notch wear. So, Q equal to Cw into h to the power 5 by 2. Cw is a flow coefficient. This is another geometry for wear, trapezoidal notch. There is rectangular wear as well. So, this is in between V notch and rectangular notch. So, some typical dimensions are shown. V stands for vertical and H for horizontal. So, 4 units of vertical length is to 1 unit of horizontal length. The relationship between the flow rate, the length L of the trapezoidal notch and the height is given as Q equal to Cw into L into h to the power 3 by 2, where again Cw is the constant or coefficient for this trapezoidal notch. I just want to show you one slide about solid flow in conveyor. Solid flow in conveyor is an important application in chemical process industry. We can measure the solid flow in conveyor by using a load cell. So, here is the load cell which measures the mass of material distributed over the length of the conveyor. So, if m is the mass of the material distributed over a length L of the conveyor and the conveyor velocity is v, the mass flow rate can be expressed as m into v by L, where m is the mass, v is the velocity and length is the and L is the length over which the mass m is distributed. So, this is how you can measure the mass flow rate for solid flow in conveyor. You can also use nuclear mass flow meter for measurement of solid flow in conveyor. The nuclear mass flow meter will make use of a gamma ray. So, gamma ray will be sent and from the other end there will be a detector which will find which will again detect the the gamma ray. Okay. So, it is obvious that such operation will involve safety concerns, because you are using gamma rays. So, use of load cell to measure solid flow in conveyor is a very convenient and common applications. Finally, we want to ask how to select a flow meter for my application. We must consider the following factors: range, accuracy and reliability, pressure range, temperature range, type of liquid such as density, viscosity, presence of particulates in the flow, where there are particulates present in the flow or not, loss of energy, ease of installation and emplacement, and finally cost. So, this completes our discussion on flow measuring instruments.